So when we did this proportions test, I made an assumption. The assumption was that we could use a z distribution. And that meant that I was assuming that these proportions were normally distributed. So the question in front of me is, how do I know? Because otherwise, I have my head firmly at my backside and I'm doing the wrong thing. How do I know whether or not our percentage, our proportion of shoppers that paid with a debit card is normally distributed over these two different years? We had a test to talk about normal distribution of a proportion last chapter, when we're just doing one proportion, checking it against the benchmark. We were able to decide whether or not it was normal based on something. It's even in the homework that I gave back to you on Monday.
What if n was greater than or equal to 30 and there's like two kids evenly symmetrically?
The n being bigger than or equal to 30, that's for a mean. But yes, that's the one that works for a mean. But this is for a proportion. We needed something a little bit different. I need to know something about n, but I also need to know something else. There should be a great flipping of notes at this point, or textbooks or something. You've heard this before. I need to know something about the numbers to be able to determine whether or not this is normal.
What's it called? It's like practically
Effectively infinite. That is only true in my sampling in the sample distribution. So yes, but we had of all possible shoppers, we took a sample of 200. All possible shots, a ton of shoppers, isn't it? So that's still sufficiently large. But it's actually more about the proportions themselves in this case. We go back up here, because that's the data we started with. 66 out of 200 in year one, and 86 out of 200 in year two. And then we checked to see if those proportions were significantly different by using this z-score. And that use of the z-score required me to make the assumption that these were normal. Why am I allowed to make that assumption? Back in chapters 8 and 9, when we were talking about proportions at all, we said we had to have a certain number of yeses, a certain number of no's. What was the magic number? This is, by the way, Jacob, this is why we needed larger and larger samples as the proportions got further away from 50%. The further away from 50% it is, the larger we need a sample we need to make sure we have enough to say it's a normal distribution. What's that enough though? 10. I need to have at least 10 in each yes pile and at least 10 in each no pile. I have 200 in pile 1. 66 of them are yeses. That's good. How many no's does that mean? $134. Similarly over here, I have 86. That's good. How many no's in this pile? Well over 10, right? If I have at least 10 in each pile, of the 4 piles I can make, then I can assume that this is normally distributed well enough to use the z-score. If not, I have to do the binomial approximation like with the eggs back in chapter 9 and 8. How many dozen eggs we were using? So this is my workaround. I can assume normality when there are at least 10. In the yes pile from group 1, the no pile from group 2, the yes pile from group 2, the no pile from group 2. Another way to think of this is that the product with the proportion is bigger than or equal to 10. And the product with 1 minus the proportion is bigger than or equal to 10. But since we defined P1 to be x1 over n1, this is really just another way of writing x1 and x2 right here. Questions? So this idea back here, this square root down here at the bottom, that's our pooled combined proportion, and that's our standard error. And that works because we assumed our variances could be combined. That in the populations, the proportion should have remained the same. But I want to think about confidence on that. I'm saying this difference between my two proportions of 10%, right? We went from 33 to 43% back in my proportions, is not statistically significant because we were able to divide out our standard error and show that that was not enough. The p-value is bigger than 0.01. I should be able to build a confidence interval. Well, really, it's not just for proportions, it's for the difference in two proportions. But I'm actually going to build this one under the assumption that I don't have the same population proportion. I don't want to pool this time. That is a horrible looking B. Combined, pooled proportion. Well, in that case, I need to treat each of the proportions separately in my standard error. So I'm going to start with the difference between the two of them, and then I'm going to add or subtract. Now, this time I'm thinking of a confidence interval, so I'm thinking of two tails. Two tails means I'm going to use the z for alpha over 2 instead of the z for alpha. And then I need my standard error. For a proportion, the standard error is you take the proportion, multiply it by 1 minus the proportion, and divide by the number of things in that group. When we were doing a benchmark, that was all we had, because I only had one number to compare it against. But now I've got two groups, so I'm actually going to put the second proportion in here the same way. And this is the unpooled version of the standard error. If my confidence interval contains 0, then I cannot conclude these proportions are different. If my confidence interval doesn't contain 0, then I can conclude these are different. That's a two-tailed test. I'd be outside z alpha over 2. I'd be in the rejection region on a two-tailed test. So every time I do a test, I have a confidence interval. Every time I do a confidence interval, I'm really doing a test. That's really convenient. Oh, again, this assumes that we are using normal populations. I got a z here, means these things still have to apply. Questions? All right. When I was doing the test for means, Leo, I was doing the test for means. You said in order to be normal, I needed to make sure that I had more than 30.
Yeah.
But even when I did all the means tests for two means, whether they were paired or unpaired, I made a comment about the variances. We had paired with unpaired with unequal variance, or we had paired with equal variance. So I got to know about the variances, right? So it would be to my benefit to figure out how to compare variances. If I have two different distributions, each one's going to have a variance. I have a mean, standard deviation, variance for each one. I could ask the following question. Which of these is more consistent? If you're on an athletic team, would you rather your defense average I'll pull a number out of my ass. Letting in 50 points a game, but it could swing as low as 10 or as high as 100, or 55 points a game, but it only swings between 40 and 70. Which is a better defense? I'm making steel rods for a construction project. They need to be 2 millimeters in diameter. And I can get an average of 2.03, but the variance is half a millimeter. Or I can get 1.96. The variance is only 0.2 millimeters, which is more consistent. Oh. Variance is what's going to tell me who's being consistent. Quality control, volatility in market returns. The more consistent defense, the guys I can count on, right? They don't let as many points through, the variation is smaller. Consistency in wait times. How long are you going to be on hold? How long is that stupid little wheel going to keep spinning as your computer says updating? I need to know if I can be consistent about these things. I need to be able to compare these variances. Ideally, I'd like to know if the variances are different enough that it matters. That's a statistically significant question. Now, if you think about this, this is really asking, is sigma 1 larger, smaller, or the same as?
Well, gee, that sounds familiar.
That sounds like a null hypothesis. And if those three are my options for the null hypothesis, then my alternate hypothesis is going to be the opposite, the completely exhausting, mutually exclusive option. So again, look at the alternate hypothesis. In this one, I'm saying that we are to the left. Sigma 1 is smaller than sigma 2. This is a left tail. Here I just want different. This is two tail. Here I want it to be bigger. This is a right tail. Now, when I look at this null hypothesis, this bothers me quite a bit. It depends on which one I call 1, which one I call 2. But left, right, two tail is going to change based on that. And I'm really not comparing to anything fixed. I'm comparing to each other. And that bothers me. So there's another way to write all three of these. That instead of looking at the variances against each other, I'm going to divide. And I'm going to think of sigma 1 squared over sigma 2 squared instead. And if I do that here, then I'm saying this is bigger than or equal to 1. And if I think of that here, it's sigma 1 squared over sigma 2 squared less than 1. Okay, I'm to the left of 1. That now makes that clear as a left tail test to me. And then here, the same thing. And here, the same thing. So if I switch these, instead of thinking of the two variances against each other, if I think of their ratio instead, I can compare to 1. And I see left of 1, not equal to 1, bigger than 1. That makes my tails a little more sensible to me. I don't care which way you choose to remember it. But this idea, when it was put forth by a guy by the name of Ronald Fisher, Fisher said, I want to look at the variations going on here. I need a distribution for variance. And the Fisher distribution is a very different looking thing. Please note, sigma 1 squared over sigma 2 squared. That number is always positive. Positive number on top, positive number on the bottom, because they're both squared, that's got to be a positive thing. So this distribution, as opposed to the z, as opposed to the t, is all on one side of 0. In the t distribution, the 0 is in the middle. In the z distribution, the 0 is in the middle. Fisher's distribution is all to one side. And Fisher said this distribution is going to really need the variances to be quite different. So the distribution itself is very lopsided. Unfortunately, I'm a crap artist, so take that with a grain of salt. The distribution itself is based off of our significance. The choice of alpha changes this distribution a lot. When alpha is large, this distribution has bigger tails, more kurtosis, as it were. When alpha is small, the tails get skinnier. And this bulge here on the left moves closer to the axis. But that's really less important. Because Fisher actually noticed that this was even more complicated. It also depended on my two sample sizes. And that meant that we ended up with degrees of freedom again. Like we did with our means, we have going to have 2 different degrees of freedom. And the 2 different degrees of freedom are going to be based off this N1 and N2. So I'll write it over here on the side. Degrees of freedom number 1 is N1 minus 1, and degrees of freedom 2 is N2 minus 1. So it's our same general idea. But look at these alternate hypotheses that are right up here. If I'm going to say the null hypothesis is true, then my result should be close to 1. And that means that the bulge, the peak in this particular distribution, is around 1. And our rejection regions, just like on the t-test and just like on the z-test, will be way out here towards the edges. Close to this side and close to this side. So we're going to do the same idea we did before. And we're going to say, hey, I'm going to need two critical values. I'm going to need a critical value over here if I'm doing a left tail test. I'm going to need a critical value over here if I'm doing a right tail test. And what do we know about the critical values? The areas outside them should be alpha. And if I'm doing a two-tail test, I'll need one on each side. And then the areas should be half of that. So here is what I get. I get a test that says, oh, I'm going to need this left F critical value. We're going to call it FL. There's the Excel command to get it. F dot inverse. I have to give it the alpha and I have to give it the two different degrees of freedom. And if I'm below that number, we should reject. Because I'll be in this little rejection region right here. If I want the number on the right, F inverse RT for right tail. Same thing. Give it the alpha, give it the degrees of freedom. If I want to do a two-tail test, I need to split that area in half. That's why you'll see here it says alpha over 2 with the right tail and the left tail. But I get an FL and I get an FR. I am much happier doing the actual calculation lookup in Excel because this distribution is rather convoluted with 3 different options. There's a table in the back of the book, but I want you to understand that the table for this distribution is going to depend on our alpha value. So there's a whole page for 0.1. There's a separate page for 0.05. There's a separate page, 0.025. And there's yet another separate page for 0.01. By the way, these have a front and a back. So there's 8 pages of tables here. Not just no, hi Al, no, I don't want to do this. I'll do the calculation part in Excel to look up these critical values. Then I'm going to need to go with this calculated value. These are going to be the F crit values. Reject, H null, when F calc is less than FL or F calc is bigger than FR. So I'm outside. But what's F calc? Fortunately for me, if we're thinking about variances, we're going to get variances for our samples. All I have to do is know what the variance is for each individual group. Then divide those. This is why I like to think of the null hypothesis and the alternate hypothesis in terms of sigma 1 squared over sigma 2 squared, because then I don't have to remember something different for the calculated F value. Now, I am the first person to tell you that reading that chart in the back of the book makes my head hurt, because they wrote a number of things in the back of the book that is different from the way I read every other table in this entire freaking book. So 99.9% of the time, I'm going to use the Excel commands to get the values for FL and FR. An example. This is 10.37, part C. This one is 67. N1 is 10. S2 is 15. N2 is 13. Alpha is 0.05. And we are asked in this particular example to figure out, is this variance statistically significantly larger than this one? And we're even told we want to do this at a significance of 0.05. So those of you with computers out, open up Excel for me. Before we calculate anything, I need to know the hypotheses, so I know what kind of a test I'm doing. Am I doing a left, a two, or a right tail test on these variances? Legitimate question. Read the question that's asked. Is the variance in group 1 larger than the variance in group 2? That is my alternate hypothesis. That's the thing I want to show evidence for. But I would write that as bigger than 1. Bigger than, that's a right tail. And that means this is H1, so the null hypothesis is no, there's really no difference in variance at anything. The top group 1 is less than group 2. Now, I need a calculated value and a critical value. Or I need a calculated value and a p-value. But p-value would require me to look up the thing I calculate in the table and figure out what the probability of that is. Mother. I hate using these tables already. So let's do the calculated version instead. What do I need to calculate in Excel? Right, I'm doing a right tail test. I need an FR value. Right tailed. I need alpha. I need degrees of freedom 1. What's degrees of freedom 1?
It would be that N1 minus 1
But N1 is right here,
or 9.
and degrees of freedom 2 would be 12. Calculate for me. Somebody give me a number.
$2.79.
Okay. 2.79. Now, just to show you, here's our table for 0.05. Degrees of freedom 1 was 9. Degrees of freedom 2 was 12. I guess they rounded slightly differently, Jacob, because I've got 2.80 here in the text.
Yeah, I mean, I round.
Right, but they rounded differently from the way you rounded, so there's a little bit of a difference. It's not that big a deal. I think it's like 2.796 or something.
It's 2.796.
Okay, well, so close enough, right?
Yeah.
Great. But that's how I would look that up. What bothers me is that the number that comes first is almost always the row number. And in this table, the number that comes first is the column number. And that makes me crazy whenever I try and read this damn table. My problem, part of why I hate doing this. That's FR. When am I going to reject?
FCF cut.
Right, but what's going to be my decision? How do I know whether or not to reject once I do that calculation? Reject if
Like these, or equal to.
I need to be on the rejection side. If we're doing a right tail test, that means I need to be to the right. So now we need FCalc. FCalc. That's S1 squared over S2 squared. Wait a minute, I have S1, I have S2, they're up there. In the data we were provided in this problem. S1 is 67. So I'm going to have 67 squared. S2 is 15. I'm going to have 15 squared. Notice I'm squaring both the top and bottom of the fraction. So I, could just do 67 over 15 and then square the whole thing. What do you get?
$19.6 Something.
Way bigger than 2.9, isn't it? 2.8. So I reject my null hypothesis. Yes, the variance in group 1 is statistically significantly larger than the variance in group 2. Question. If I had asked the question differently, maybe I'd switched group 1 and group 2 in my lists. Then I'd be doing another different tale, wouldn't I? But if I go back and I look at the table in the back of the text, I notice the picture up here. And the picture, just like in the normal distribution, just like in the binomial, helps me remember what the F is going on here. But on Tish, this is always giving me values of FR. This table doesn't give me FL. It only gives me right tail values. So how do I get left values if I need to do a left test? What, I'm completely screwed here? Well, no. Because the other thing Fisher noticed is that this graph is not truly symmetric, but it is related. If I want FL, I can get it from FR. For a given alpha and a given set of degrees of freedom. I can think, as long as I fix alpha, I can think of FR as really using those two numbers, right? This one tells me which column I'm in the table. This one tells me which row I'm in the table. But if I want FL, I'm going to flip these two. And I'm going to flip the whole thing over. So that means I can get the FL values out of this table. Again, that's a pain in the neck. And while I appreciate doing that, I'd rather just look up the FL and FR values out of Excel. Then I don't have to remember which DF goes where. I just always put DF1 first and DF2 second. Question. If I switch group 1 and group 2, that switches which is on top and which is on bottom in my calculated value here. Right? Because we did sigma 1 over sigma 2. And we did S1 over S2. So really, switching that fraction is where the flip comes from. That's why I get a 1 over here. But it is possible to always do a right tail test. There's this idea called a folded F test. And that means that I can use the table exactly as is. I don't have to mess with it. It always requires me to simply put the larger variance on top. Now, in our case, we did have the larger variance on top. We had 67 on top and 15 on the bottom, right? So I had rigged that one to already be a right-tailed test, and it was in the correct orientation to do the folded version. I cannot do the problem I just showed you in Excel. I can do the lookup for the F values, but I can't actually say, hey, Excel, calculate the F test for me. And I can't look up a p-value that way. But if I have the whole data, well, then Excel will let me do this test. Because in Excel, under my data pile, data analysis, under this giant list of tools is an F test. Right there. 2 sample, 4 variances. If I have all the data, rather than just the summary statistics, it'll do this. It always does the folded version. It always does a right tail test, but it will give me the p-value directly. And that means I don't have to compare whether I'm looking at lower or higher. I'm always looking at higher on the F versus the F critical. And I'm always looking at that p-value. If the p-value is small enough, then I'm going to reject. Question? There is always, as we did with the means, as we do with the proportions, asking the question, is this just statistically significant, or is there a practical importance to this? How much is the variance difference going to matter to my situation? The very first z-test we did on means was about lake contamination, right? Milligrams per liter, something like that. So is the change in pollution not just statistically significant? Is it actually really important to the environment of that lake? Makes a difference. This is the end of the material for chapter 10. And that means that this homework is due on Monday. And that means the exam that covers chapters 8, 9, and 10 is a week from today on Wednesday. The review sheet is posted. You get another formula sheet. You're welcome to use the one from exam 2 and a new one. I don't know what you'll find useful on the one from exam 2, but there's a bunch of stuff there that you might find helpful. Don't rewrite the one from exam 2. Write yourself a new one, chapters 8, 9, and 10. I will see you all on Friday. Have a wonderful rest of your day.